Hello. In our video today we're going to look at the product and the quotient rule for differentiation. Now product is a mathsy word for multiply and quotient is a mathsy word for divide. So what we're going to be doing is looking at rules for when we have things multiplied together and we have things divided by each other. So I have my two rules written up here, and we find them on page 25 in our log tables along with the rest of our differentiation rules. Anytime we see differentiation, we immediately open up page 25 in our log tables. And the rules are here. If I have y is equal to u multiplied by v, two functions multiplied together, the derivative is going to be u dv dx plus v du dx. So that is our multiplication rule, and our division rule, our quotient rule, is if y is equal to a function divided by a function, and we can't simplify it down, then we use our bigger rule here, v du dx minus u dv dx all over v squared. So let's put these into practice. So I have y is equal to these two brackets multiplied together. Now I could just multiply those brackets out and do the normal differentiation that we have already got practice at, but we will very quickly run into functions that we cannot simplify by multiplying out. We'll have to use the product rule. So it's good initially to practice these now using the product rule, so that when we get to more confusing looking functions, we have this rule already practiced in stuff that's a bit more familiar to us. So for right now, we can practice using the product rule, though we know, and we can double check our answers by multiplying this out and just using our normal power rule differentiation. But if we're going to do the product rule, what we do is set our u as being our first term and v as being our second term of the stuff multiplied together, and we're going to explicitly write this out. This is a highly structured bit of work, and so is the quotient rule. In fact, in some ways the quotient rule is even more so. V is equal to x minus 1. Now this is all in power notation, so we don't need to do anything other than get the derivative. So we're getting the derivative of u. We're used to getting the derivative of y, but we can get the derivative of anything we like, and we're getting it with respect to x. So we're starting with the function u, and we're getting the derivative with respect to x. The x is the thing that's being worked on. So I do my power rule, I multiply by the power and then subtract 1 from the power, so I end up with 10x. My constant just ends up being 0, because derivative of a constant and doesn't contribute to the slope, and remember we're always dealing with slopes when we're getting du dx or dy dx. And dv dx, getting the derivative of v with respect to x, is just going to end up being multiplied by the power and subtract 1 from the power. We just end up with 1. So those are the different components that I need for my formula. So my setup is always going to be the same. Define what u and v are, write down my product rule formula, write down the bits I need for my product rule formula, and then sub into it. And if I follow those steps, these questions are very straightforward. So then my dy dx is just going to be u 5x squared plus 2 times dv dx, which is just 1, plus v x minus 1 times du dx, 10x. And I multiply that out now. All the differentiation is done. This is just simplifying terms now. So I have 10x squared plus 2 plus 10x squared minus 10x, and I am left with, I have my like terms, and write everything in order, x squared and then x and then constant, sorry, 15, 15x squared minus 10x plus 2. And that is my dy dx. This is the function that gives me the slope of the tangent to my curve at different values of x. And that is what we need for our product rule, and by all means multiply out the brackets and show yourself that you get the same result. But it's important we practice this product rule now because we'll have to use it sometime later on. The quotient rule is a little bit more complicated looking, but the setup is identical. So if we have a situation like y is equal to 2x squared minus 3x all over 5x plus 7, we'll say that this top term is our u and our bottom term is our v. U will always be the top term, v will always be the bottom term. Do the same thing as we did for our product rule. We're going to break stuff up. 2x squared minus 3x, and our v is going to be our 5x plus 7. We get our du dx, and we do that again because we can see what is in our formula. So how this question will work is you write down your function, write down what u and v are going to be, go to the log tables, write down your formula, and see what you need for subbing into your formula. Then explicitly write this down, broken up like I have broken it up here. So multiply by the power and subtract 1 from the power. The constant goes to 0. dv dx is going to be just 5. Multiply by the power and subtract 1 from the power, and the constant goes to 0. So this is all of the terms I need for my dy dx. So dy dx, subbing into my formula, is going to be v du dx minus, this time, u dv dx all over v squared. So this is what we have for our, all of the differentiation is now done. This is the function that gives us the slope of the tangent to this curve at different values of x. So all we have to do now is simplify that down a little bit. We don't want to leave any brackets or anything lying around. So we end up with 20x squared plus 28x minus 10x squared plus 15. Gather your like terms. Sorry, we have the bottom line. I haven't multiplied out the bottom line because by convention you can get away with not doing so. And it's also good to simplify this and see if there's a common factor, which is a lot harder to see if we go through the process of multiplying out. So I end up with 10x squared dy dx, just rewrite that, is equal to 10x squared plus 28x plus 15 all over 5x plus 7 all squared. And though we often would multiply out our brackets, you can get away with leaving it in this form where we have multiplied things down a little bit. There isn't an obvious common factor that I can see there, so I'm going to leave that as is. If I'm asked to just get dy dx, so long as I've done a little bit of tidying there so it doesn't look like a complete mess, I get my full marks. Now I want to link back in because this has gotten really messy. This looks like a nightmarish function. And I want to link back in that this is a function that gives us the slope of this curve at different values of x. To do that, I'm going to pick a value of x that's easy for me to show you, which is going to be x is 0. So if I have dy dx at x is equal to 0, I sub in my 0 in here. So I'm finding the slope at a particular value of x. All over 5 by 0 plus 7 squared gives me 15 all over 7 squared. Approximately gives me 0.31. Now what does that tell me? that tells me that the slope of the tangent to the curve, or the slope of the curve of this curve here at the point when x is 0 is going to be 0.31. And I'm going to show that to you on GeoGebra. So again, what we found is we have our original function here, and what is the slope of this function, or the slope of the tangent line to this function when x is equal to 0. And this should be the slope. The screen is about to get brighter. So the green line here, if I turn that off for a second, the green line here is our function that we started off with, and I've called it g of x here. And that is the curve that we started out with, and we found dy dx, which gives us the slope of this curve at different values of x. And I subbed in x is equal to 0, which is where my point A is. I can see my x value for A is 0, and the tangent at that point has a slope of 0.31, just like what we found from the algebra. So dy dx when x is equal to 0 is 0.31. That's the slope of the tangent line to the curve at that value of x. And the function that we found gives us the slope for different values of x. As a quick reminder on functions, this function has some discontinuities in it. The obvious one is going on here, and that's going to happen when x is minus 7 all over 5. We'll end up dividing by 0, and we can see that we get an asymptote at x is equal to minus 7 all over 5. So spotting that type of functions work in the middle of differentiation is a good habit to be in. It's not part of the immediate question, but it can be on the exams. So we have a discontinuity because we'd be dividing by 0 when x is equal to minus 7 all over 5. And that is, if we go back to our original work, that is our product where we're multiplying terms together, and quotient where we're dividing terms. For our brackets here, we could have just multiplied this out and used our normal power rule, but we need to practice the product rule for our situations where we can't do that. So that's why I've done this out using the product rule. For the quotient rule, if we can't simplify our fractions, if we can't divide this out so that we get something that isn't a fraction, then we have to use our quotient rule. And again, our dy dx is always giving us a function that gives us the slopes of the tangents of the curves, or the slopes of the curves at different values of x. And as the maths gets more complicated, it's important to hold on to that so that if we're not getting lost as to what we're actually finding. And that's what we need for the product and the quotient rule.